Okay, today we're going to talk about special right triangles, and this is actually one of my favorite things to do in person and actually have a square and have an equiangular and equilateral triangle and cut them in half and have a flashcard made, but we're going to do our best virtually on our whiteboards. So, obviously what we're looking at here are not right triangles, but they're very, very familiar shapes to us. This one, because it has four congruent sides and four right angles, we know that it's a square. So if I were to cut my square in half, okay, and only focus on half of a square, what do we know about that special right triangle? Well, obviously it's a right angle. Obviously we have two congruent sides, so it's an isosceles right. And remember, if it's an isosceles triangle, it means that these two corners are also equal. Well, if this is 90 and these two are equal, they each have to be 45 degrees. Okay, so if I take a square and I cut it in half, I have what we call a 45, 45, 90 triangle. Okay, and again, we said we know that these two sides are the same. I'm actually going to call them A and A. You can call them anything you want, A and A. But I want to know, what is this third side? Okay, well, it's a right triangle, so I can use the Pythagorean theorem. Usually I'd say a squared plus b squared equals c squared, but these are the same. So I'm going to say a squared plus a squared equals c squared. Well, what's a squared plus a squared? It's 2a squared. And remember, my goal is to get this c by itself. What is the hypotenuse of this triangle as it relates to these other two sides? Okay, so if I want to get this c by itself, I'm going to take the square root of 2a squared, and I'll get c, okay? But the square root of 2a squared is the same as the square root of 2 times the square root of a squared. And if I have any number, then I square it, and then I take the square root. I have 5. 5 squared is 25. Square root of 25 is 5. I just get that a value back. I'm going to swing that a value to the front so it doesn't get confusing as to if it's under the square root or not. And I get a times the square root of 2. And so what we just showed is that in any 45, 45, 90 triangle, the two legs are the same, and the hypotenuse is always that leg times the square root of 2. So this is where this could be helpful. Pick any number in the world. Okay, and if I know it's a 45, 45, 90 triangle, let's say that I have 12. Okay, I know that the two legs are the same. So as soon as I see this 12, I know this also has to be 12, right? Those two have to be the same. Well, what's this third side? It's just the leg times the square root of 2. It is 12 times the square root of 2, okay? If you were to get a decimal approximation, 12 times the square root of 2, it's approximately 17.0, okay? If you were to do Pythagorean theorem, 12 squared plus 12 squared equals c squared, you should get that c is approximately 17.0. If you were to do the sine, I should probably say cosine, of 45 degrees, I'll put the 45 in here, and it is cosine adjacent 12 over x, and you solve that for x, you would get approximately 17.0. Okay, so the point is, if you like to study that this triangle always has a, and a squared of 2, you can make certain problems much, much faster than Pythag or SOHCAHTOA. Okay, let's look at the second special right triangle. This time we don't have a square, obviously. We have an equiangular triangle. And we know if all three angles in a triangle are equal, they would all be 60 degrees. Okay, I'm not going to write it in all. They're all 60 degrees. And we also know that the three sides also have to be the same. But I'm going to do the same thing I did to the square. I'm going to cut it in half. Okay, so we're only going to look at half of the equilateral triangle. Okay, so again, this is 60 degrees. If I cut this in half, this used to be a straight line. A straight line is 180. Half of 180 is 90. So this is a right triangle. If I have a 90 degree and a 60 degree, I have to have 30 degrees up here in order to make it be a triangle. And I know it's hard to see from the picture, but this is the short leg across from the small angle, and this is the long leg across from the big angle. Okay. Well, what do we know about the side lengths? We don't know a whole lot about the long leg right now, but we do know that this whole side is the same as this whole side. But what did I do to this side? I cut it in half. Okay. So I'm actually going to call the bottom or the short side B. Okay. And how is this hypotenuse related to this? Well, look, if this is B, I cut it in half. This is B. The whole thing is B plus B, or 2B. That means this side was 2B and this side is 2B. But again, I'm only looking at half. So I see 2B, B, and we don't know. So what am I going to do? I'm going to figure out what this side is. And again, we have a right triangle. So if I use Pythagorean theorem, it is b squared plus something squared is equal to 2b squared. Okay, well, b squared, there's nothing to do there. Plus, we don't know squared, is equal to, now when I square this, remember it's times itself. 2b times 2b is 4b squared. And I'm trying to get this question mark by itself. I'm going to subtract b squared from both sides. 4b squared minus 1b squared, those are gone. So question mark squared is equal to 3b squared. Well, how do I unsquare something? I take the square root. So the question mark, or that long leg, is equal to the square root of 3 times b squared. Now remember, in the last one I said we can separate this, right? And something squared and square rooted, the square roots and the squared cancel each other out. So really that long leg is b times the square root of 3. Again, I just put the b in front so we're not confused as to whether or not it's under the square root. It is not under the square root. So what I get here is b times the square root of 3. Okay, and again, the reason we're doing this is sometimes it's nice to know shortcuts. This is giving us a shortcut. I know this stuff doesn't feel like a shortcut, but at the end of the day, if you memorize these two blue triangles and their patterns, short leg is b, long leg is b times the square root of 3, and the longest side, the hypotenuse, is always 2 times b. If you find the short side, the other two are easy. Here's what I mean. If I have a 30, 60, 90 triangle, okay, so let's say I know that's 90 and I know that's 30. Again, any number in the world. We'll go with 12 again, okay? Well, 12 is equal to b, right? 12 is equal to b. It's the short side. It's the one that's across or opposite from the 30 degrees. How do I find the hypotenuse? Well, that's 2 times b. 2 times 12 is 24. How do I find the long leg? Well, that's b times the square root of 3, or 12 times the square root of 3. It's a very, very short way to find what I'm missing. Okay, so let's look at some examples here. I'm going to spread this out, not knock over my water. Okay, spread this out a little bit so you can see my 2 blue triangles. Okay, my 2 blue triangles. I might even get rid of this so it's less confusing. Okay, if I look at example number 1, first of all, I have to identify, okay, I know it's a right triangle. Ooh, these are the same. If it's an isosceles right triangle, then I know it's a 45, 45, 90. 45, 45, 90. It has to be if it's a right triangle. Okay, and really without doing much work, you should say, okay, the 2 legs are the same. Okay, if this side's 29, then the other leg is 29. Now I might have to rotate this one so I can see a little bit easier. Of course I didn't erase all that stuff. Okay, so if I'm reorienting my triangle, I can see this is A, and this is A times the square root of 2. Okay, well what's A? A is 29. So this y value is really 29 times the square root of 2. Again, you can use Pythagorean theorem, you can use SOHCAHTOA to find this, but that's a pretty quick way if you know the special right triangle pattern of a 45, 45, 90. Ooh, I forgot to tell you what this one's called, but I bet you can guess. This one is called a 30, 60, 90 triangle. That's the other special right triangle. 30, 60, 90. So if I look at example number 2, I can't just rotate this around because then I'd have to flip my board. This is where I really like to have an index card or something. But what I can do here is I can say, okay, if this is 60 degrees, what is across from 60 degrees? That is b times the square root of 3. Okay? If I know this is 90 and I know this is 60, it has to be 30. Okay? The hypotenuse across from the right angle is 2b. And the short leg, the only one left, or the one across from 30 degrees, is b. So in this case, we know b is 7. That makes the other two pretty easy. 2b, 2 times 7, that's 14. b times the square root of 3, 7 times the square root of 3. Again, you can use Pythagorean theorem, you can use SOHCAHTOA here, but it's a lot faster if you have studied the patterns. Okay? If this is super duper confusing and you just want to use, let's see, the sine, sine's not going to work here. Let's do cosine of 60 degrees is equal to 7 adjacent over y, the hypotenuse, and you solve this using cross multiplication, you will get that y is equal to 14. Okay, and it's okay to use SOHCAHTOA. And once you have two sides of a right triangle, it is absolutely okay to say 17 squared plus x squared equals 14 squared. I guarantee you're going to get 7 root 3. Your calculator's not going to say it like that, okay? It's going to be in decimal form. Your calculator will tell you approximately 12.12, okay? Last example, example 3, again, we can see it's a right triangle. This time, we're given this longest side, the hypotenuse. Well, what's the hypotenuse? It's 2b. Okay, well that's easy enough. 16 times 2b, b must be 8. Okay, the short side across from the smallest angle must be 8. Okay, what's the long leg? It is b times the square root of 3. And now that we know that b is 8, x is 8 times the square root of 3. Okay, so these two special right triangles can help shortcuts with certain right triangles.